This talk is about first observation of aromatic bond density, which you can find in paper by Rosalind Franklin, mostly forgotten at this time. A disclaimer, this is a technical note containing no new concepts or new software, so whatever I am mentioning here is already published or more or less known. The paper I'm talking about is a letter to the editor of Nature. One page, you can see it, the whole here, with one paragraph in the next page. Came out in January of 1950, titled Influence of the Bonding Electrons on Scattering of X-ray by Carbon. When I'm saying forgotten, I mean that citation count is 11 in scientific publication. Plus, of course, in all biographies of Rosalind Franklin, there is a full list of her publications, which adds up to 24 more. So, what is inside of this very interesting one-page note? First, some historical picture. Most of books on charge density mentioned that first observation was done by Sir Bragg in 1920, when
something happens to sound.
Yes, I don't have any sound.
No sound.
Is the sound back? Do you have the sound now?
No.
Oh, that's also because I paused it. So if you can hear me, speak over it if you hear it now.
Yeah, Reininger.
Okay, it's back.
Okay.
Famous paper in Science for Physics that explain that very reflection of diamond as Reininger effect, the effect of secondary scattering of X-rays. That is why all these explanation of charge density became unreliable and honestly should be abandoned. The real picture of diamond came out only in 1960s by Braille, and it was very similar to the Dr. Franklin's paper I'm talking about. So by the time Dr. Franklin did her work, it was no reliable data about covalent bond charge density. The object of study was graphite, and the structure of graphite was known Bernoulli structure, which was done in year 1924. After work of Dr. Franklin, there were several more attempts to do graphite. All of them are wrong, including Linus Pauling publication in 1966. I'm saying that just to highlight it's not trivial. The full bond density picture for diamond came out in 1973, and for graphite in 1978. I'll show you this. The nature of chemical bond at this moment in 1949 was mostly descriptive. Huckel method for aromatic bond was described in 1931-1937 papers by Huckel, but was mostly unknown in English-speaking world. Pariser-Parr-Popel method was yet to come. The paper itself was probably written in spring 1949 or even earlier. We know that because there is a letter by Professor Coulson, which was the head of theoretical physics at University of London at that time, thanking for sending me a copy of letter which you are offering to nature. I read it with very great interest. Obviously, letter was written in June 11th, 1949, so perhaps last day of May or first day of June, when he received the copy of the manuscript, which means the manuscript was available in May 1949 or even earlier. We can also see the first very positive response to the manuscript even before publication. Now, what's special with graphite? Here is a ore tap of graphite made based on neutron structure done in 1975. Both of carbon atoms are on fixed position. You do not need to refine them. They are two anisotropy parameters for each carbon atoms, but they are essentially the same for each of them. A little surprise, because the plane moves mostly as a whole. So technically, you need to have only two independent parameters to describe all crystal structure of graphite in independent atom model, which makes it very attractive if you have good data. Unfortunately, in reality, this is problematic. So, what are main points of Dr. Franklin's letter to the editor? First, it seems that an enormously high intensity of 100 line must be attributed to configuration of valency electrons in graphite to carbons containing incipient graphite layers. We are seeing that intensity changes with configuration of valency electron, first time written. Now the same carbon, the only 100 reflection occurs in angular range at which L electrons make appreciable contribution to atomic scattering. This is very important observation, which is well known but often forgotten. What happens with scattering factors with angle? Here there is my example of addition of one electron to atom of oxygen. So this is oxygen atom, red is oxygen ion. Effect of 1 2p electron added. You see that visible difference is only at sine of theta over lambda well below 0.2. It's very important. Even when you do large molecules, we often do not measure reflections at small angles well enough because of beam stop problems. When we do crystals of diamond and graphite, even the first reflections are far away from this region. And graphite, as you can see, is far more suitable than diamond for seeing effect of p electrons. This was quickly supported by neutron diffraction data by Bacon in November 1950, who mentioned that Franklin shown an anomalous twofold increase of X-ray diffraction intensity, and his data supported this. Next, very important point, electron density for sp2 electrons lies midway between two carbon atoms. And now let's look at more precise data, which were measured 30 years later. And we can see that indeed we have visible peaks between carbons, and these peaks have high intensity and lie exactly in the middle. So to correct them, we need, as Dr. Franklin did, to put additional scattering here in the middle to remove this deformation density. This was done by Moss, who supported Dr. Franklin's data and gave reference to her work, and also by Chen, Trucano, and Stewart, who did it even better with full charge density study, but did not refer to Franklin's paper. Let's look how these approaches lived after. The bond scattering can be applied as a single scattering center, same as in Franklin's paper. And it was done for diamond by Brill in 1960 by applying one single Gaussian describing the movement of electrons with no reference. Again, Coppens in 1974-1976 was studying deformation peaks and using one single scattering center in the middle as a Gaussian, and didn't give a reference. The same approach was done by Afonin and a number of co-authors, and this approach ended up as high-resolution model and Phoenix refined, so you can use it if you have this software. Virtual atoms are embedded in MoPro charge density package, and there are plenty of publications using the virtual atoms approach. Let's look how we can do it using simple Shell software, for example. For atoms, we are using Kramer-Mann scattering factor, in which coefficients A, I, and C are number of electrons. By adding additional anomalous scattering center, we cannot change number of electrons. So we put our scattering intensity as an anomalous scattering in position 10 of scattering factor line in shells, and we put a name of element. Some software accept any names. If you are using OLEX2, you name it helium because it will not accept unknown atoms. Then you rewrite your data file you have with usual refinement and add a part describing these new scatters that you put between carbon atoms, exactly as it was advised in Dr. Franklin's note. So we are putting 6 here and 1 here, and we assign, of course, variable intensity because we do not know how many electrons will play a role here, and we put variable Debye-Wheeler factor. What will be the result? Let's look at biphenyl molecule. Here you can see the peaks of residual density exactly as they were for graphite. Independent atom model with spherical atoms give us very nice structure, but with abnormally high R factor. If we correct it at bond scattering, we have dramatic decrease of R factor and much better standard deviation on bonds. Resulting difference map has practically very small and very random peaks on it. Another way, we can look at difference map peak here, which disappear after applying bond scattering. If you do full-blown quantum crystallography with Hirschfeld atom refinement, we have something better than our very simple approach, but this difference is not dramatic. Now, when we reduce quality of our experiment artificially, so resolution is 0.8, we still have the same difference. We still have the same effect. We just do not see it. And this clearly supports this statement. Yes, you need to look at low angle reflections. That's where the bond density is. The same is the picture for all aromatic compounds. We have dramatic drop of R factor and improvement bonds. The same we see at larger organic molecules. We have improvement of R factor to the level of heart, and we have better bonds. In case of famous lead molecule, we again have the same picture. And if we compare with heart, with new Nosferatu method, or with MOPRO, we see that we can have even better R factors. As a result, we have very simple approach for removing covalent bonds and lone pair residual density. No pre-calculated parameters from DFT and other sources are necessary. We use the same software with no modification, shells, OLEX, Refine, or YANA. You can stop at any level of correction. You can make all your bonds different, keep all bonds of the same type the same. You can apply bond scattering correction to a fragment of a structure, mostly aromatic. No, you cannot calculate real location for hydrogen atoms. If you want, you need to change scattering factors for hydrogen, and this is a separate story. It will not work for heavy atoms, but this restriction is the same for any other procedure. Of course, it will not work on low quality data. You cannot correct that data set with a good model. Now, this is not charge density. If you want charge density proper, you certainly need to collect better data and use charge density software. And this is 70-year-old approach. So, what we see from our one-page letter to the editor written by Dr. Franklin in 1949, the first observation of aromatic bond density, 100%. Most probably it was the first observation of covalent bond density because previous diamond data are ambiguous. The first observation based only on intensities, not on forbidden reflections. Next, statement of importance of low angle reflections for charge density observation. Same is true for hydrogen atom for the same reason, no correlations. And very important, simple but powerful tool for removal of residual bond density. It's quite an achievement for one page of text. On psychological level, an important take-home message is science is done by young people.